For this tutorial, I'm going to be talking about how we work with force diagrams, which are a way to represent the forces acting on an object. To do this, I'm going to use one of the examples that we used from class. So this was the example where we had the person that was starting to jump and right after they had jumped, and we'll deal with those two situations to show the difference in what's going on in both of them. So let's begin with the person right as they're starting to jump, and so we've got the person shown to the left here, ready to, with their knees bent and ready to spring themselves upward. There are a couple different ways that we can think about this. We can think about this in terms of the individual forces we know are going to be working on the person at this time. And we can also think about it in terms of the net force. What is the overall combination of the forces acting on this person, and trying to get some information on that. In general, we're going to have to use some kind of combination of both of those to get the full picture of what's going on here. So let's just dive right in. When we have a person who's standing on Earth, we know that pretty much wherever they are, there's going to be gravity acting on them and pulling them down towards the center of the Earth. So we can go ahead and start this off by putting in a downward force here, representing gravity. This is just one thing that we know, that since objects will attract each other through gravity and the Earth is very large, it's going to have a decent tug on the person. We can also think about what else could be exerting forces on the person. So we'd look around in the diagram and think about what this means, and we can see that the person is standing on the ground. Because they are on the ground, it is very likely that the ground is exerting some kind of force on the person. In this case, it's supporting them, it's holding them up, and so we can think about this as there being an upward force from the ground. So we can draw that as our first picture of what's going on here. What gets a little bit more difficult, though, is thinking about the relative magnitudes of these forces. Is gravity going to be stronger? Is the force from the ground going to be stronger? And this is one of the limitations of starting with the individual part, because we don't necessarily know that. And in order to figure that out, we're going to have to go and look at the net force. As we've mentioned in class, net force is very closely tied to acceleration. So we start thinking about what the acceleration is going to be for the person in this situation. It may be a little bit difficult to think about this just conceptually, but we can use some equations to give us some kind of indication, even if we don't know any specific numbers. What we can do is just plug in some numbers that seem to make some kind of sense to see if they tell us something about whether we should have no acceleration, whether it should be positive or negative, and that can give us an idea of how to get going. To do this, we can work with our equation that acceleration is equal to final velocity minus initial velocity over time. We'll then need to think about some reasonable values that we could put in for the two velocities and for the time. Now, when this person is starting to jump, we can think of them as, being in that crouch position, getting ready to spring upward, but they haven't actually started yet. And so at that point, they're not going to be moving, they're just going to be ready, which means that the velocity then would just be 0. This tells us that we can plug in a 0 for our initial velocity, which will be on the right in this formula. As for the final velocity, they will be moving by the end of this springing, so we know that they're going to be moving upward. They're pushing themselves upward. If we defined up as the positive direction, and so I'll put this on the diagram that going up is the positive direction, then that means that this person will end with some kind of positive velocity, and we can just put some kind of number in for that, maybe 2 meters per second. Meters per second being an appropriate unit for velocity. As for the time now, it probably won't take them too long to do this, so maybe we could just put in, say, 5 seconds. That's probably being a bit generous, but again, this is just trying to get some idea of what the sign will be, because that can tell us a lot here. We do know that the time is going to be positive. The time is going to continue along in the positive direction here, so that value is, if a little large, at least reasonable. When we solve this out, we're going to end up with a value that is 4 meters per second squared, which would be our acceleration based on these numbers. Now, the number itself, not all that important, but what we do see is that it's a positive value. This makes some sense. If the person is stopping and then they start moving so that they're going upward, that they're going to be accelerating in the upward direction. If they are accelerating in the upward direction, that means there should be a net force in the upward direction, a positive net force. So we can go ahead and draw on our diagram that there's going to be some net force. which is going to be shown in the upward direction. So I'll put that on our net force diagram then. Now we've got that, let's go back to our individual force diagram to see if we can refine that a little bit more. We have just said that there's going to be some net force in the positive direction. Because there is a net force, that means that the two individual forces here cannot completely cancel each other out. Based on the way this was originally shown, the size of the arrow seems to be pretty similar, but we now know that they shouldn't be. One should be larger than the other. Because the net force is in the positive direction, that means that the stronger force in this case should also be in the positive direction going upward. That's because in order to cancel out the downward force and to still have some left over so that we have a net force in the positive direction, it needs to be a larger force. We can show that by extending the arrow so that it would now look something like this. We have a much longer arrow representing the force from the ground pushing us up. And we can see that this is now consistent with the net force being in that positive direction. So that takes care of this situation. We used the acceleration of the person to find that there was actually a net force in the positive direction, which then helped us to see that the forces from the ground and gravity should not cancel each other out, with the ground force pushing up being stronger in the case. In the next video, we'll assess the second case once the person has jumped and is in the air and see what forces are acting on them at that point.